Hello, everybody, and welcome to another wonderful day of chemistry. So today we finally get to talk about chemical reactions. So let's go ahead and go with a brief overview. What chemical reactions, why are they important, all that jazz. So one of the biggest defining features of chemistry is this idea of chemical reactions. It's this bit where we go from alchemy to chemistry. And the important feature of alchemy that stayed with chemistry is it's about trying to figure out how we can transform one thing into another, which is kind of its own form of magic. That what you start with isn't what you have to end. Whether it's something like metallurgy of turning rocks into steel, or whether it's cooking, like turning flour into a cake, which when you think about it is a little weird. It's all really chemical transformations. So let's go ahead and go back to Dalton, as we tend to do, and think about what a chemical reaction is. So the idea is during a chemical reaction, we're not creating or destroying matter. All we're doing is rearranging it from one substance or phase to another. So let's think about that classic children's chemical reaction. Baking soda, acid, put them together. You end up producing CO2, water, and salt. The salt produced will change depending on which acid you use, but it's actually kind of cool. We take a solid, we add something that's dissolved in a liquid, and we end up producing water and gas. So we have this visible change in what we're working with. And there's something, when you think about it, that's still as exciting about that as it was when you were a kid. We get some sort of transformation in matter. Now, one of the very cool things that really helped develop chemistry is that a lot of these rearrangements can either release or absorb energy. And it was this idea of chemical reactions releasing energy that drove essentially the modern age as we harnessed the magic of fossil fuels to release energy that have driven us forward. However, we need a good idea of chemistry in order to find new reactions that can release energy so we can keep our modern life. And again, being able to understand how energy and matter flows is going to be an important thing to honestly be a good citizen in the future. Now, one of the most important features is that there's going to be a lot of rules that with regards to what reactions can occur and which reactions can't. And one of the things that makes this a real hard science is that we're going to also have to be able to understand these relations, use them to make predictions, and when possible, quantify, which I know scares many, but it is an important ability and again, a real magic of chemistry as a field. So let's go ahead and start with some good key signs that a chemical reaction has occurred. And when these happen, it almost always entails some sort of chemical reaction. If you have a release or an absorption of heat, this almost always includes a chemical reaction, and at the very least, usually regards some sort of phase change. We've got color changes. This means that something has happened to the molecules present where they went from being able to absorb light to not, or vice versa. Similarly, if you have an emission of light, it usually indicates some sort of change in the matter present, or at least in how the electrons are moving. A formation of gas. Well, I created gas molecules, so something's happened at a chemical level. I took a solid, a liquid, a dissolved species, and I put it into the gas phase. And finally, forming a gas is a reaction, so should forming a solid. So we're going to be looking at chemical reactions in this chapter that kind of embody most of these. All right, now let's go ahead and look at how we represent chemical reactions. Classic way we represent them is with chemical equations, also known as chemical formula, reaction formula. They're all pretty much the same thing. And the key defining feature of a chemical equation is going to be this reaction arrow. So this denotes that I started with something and I made something else. So some sort of chemical reaction has taken place. So in this notation, the left side represents what I started with. So we call these the reactants. and they will essentially disappear as the reaction occurs. On the right side, we have the products. So this is whatever is generated over the course of the reaction. And the amount of each of these should grow as the reaction takes place. And in the middle, essentially, according to Dalton, what we should see is that the atoms present at the beginning of the reaction should also be present at the end of the reaction. So sometimes a good way to look at this reaction arrow when we're looking at a reaction as an equation is as an equal sign. I should have the same number of elements of each element on the left as on the right. I start with 2 sodiums, I end with 2 sodiums. I start with 1 carbon, I end with 1 carbon. I start with 3 oxygens, I end with 3 oxygens. Now the arrangement of these atoms can change, but the overall number won't. And we can also use this to predict how much of a given species is being consumed and how much of it is being produced. So let's go ahead and look a little bit more at this. So you'll notice that not only do we have the chemical species, we also have these notations in parentheses. These essentially represent the phase of each chemical species. And one of the reasons why I chose this reaction is because it includes the 4 phases you're most commonly going to see in a chemical reaction. A solid, like baking soda, a liquid, like water, a gas, like CO2, and here's one that you may not have seen, aqueous. So this simply means something that's dissolved in water. So in this case, we start with an acid, which is likely going to be added, dissolved in water, and we're going to end up with dissolved salt. More or less think of this like seawater, salt dissolved in water. Now, one of the things that often a lot of lazy students do, and Lord knows I did it when I was an undergrad, is forget to include the phases. But you really can't, because it's important to note that phases have very different reactivities. I'd expect a very different reaction if I'm producing liquid water than if I'm producing steam. I'll tell you what, it definitely would be at a much higher temperature. Or if I'm producing ice, which, let's be honest, would be a little bit weird. But some reactions do that. And it's going to change all of the dynamics. And it might not always be as obvious as it will be in this reaction. For example, sometimes I might be producing enough sodium chloride that I'm producing a solid. In this case, because I'm producing water, it's probably being dissolved, but that isn't always a guarantee. So precision is very important. When working with numbers, we have units. When working with chemical equations, we have phases. Don't forget either. Now, when we're working with these phases, it is worth noting that we can kind of predict in general which parts of the periodic table will have which sort of phases. So in general, acids are always going to be aqueous, pretty much unless you see explicitly stated otherwise. You may see some acids that can maintain multiple phases, such as HCl, which can actually volatilize, also known as produce a gas fairly easily. But most of the time, when it reacts as an aqueous species. It reacts as part of water. Metals, at least in their elemental form, are almost always solid. The lone exception is that oddball mercury, which is a liquid. Most of our nonmetals are almost always going to be gases unless stated otherwise. And metalloids, so here in the middle, they tend to need to be specified. And molecular complexes, well, those get a little bit messy, and we'll try and address them as we go forward. So next time, we're going to be trying to figure out how we can turn basic descriptions of chemical reactions into a quantifiable chemical equation and show basically how we can put it to use. Until then, take care.